Welcome back to The Explainer, everyone. Today we're taking a trip back to the year 1900, and I want you to really picture the scene here. Physicists at the time, they were feeling incredibly confident. They genuinely believed they had the universe basically solved. They had Newton's laws all figured out, they completely understood electromagnetism, and honestly, it felt like physics was just wrapping up. The general consensus was that there was literally nothing left to do but measure things a little bit more precisely. But lurking right there in the shadows of all that supreme confidence was a completely catastrophic error.
So, what if a warm cup of coffee could just vaporize you? Now, I know that sounds absolutely ridiculous, but there was this one tiny, super annoying puzzle regarding the color of hot objects. It really seemed like a totally minor footnote at the time. But when physicists actually sat down to solve it, their equations didn't just give a slightly wrong answer. They gave an answer that completely shattered classical physics, an answer that literally suggested everyday, warm objects would instantly destroy you.
Okay, let's dive into this. Section 1, the one small problem, or heating up reality.
To really grasp what was going on, we need to start with something completely grounded, an everyday phenomenon that every single person back in 1900, and us today for that matter, is deeply familiar with. Heating things up. Just think about a regular stove burner, or maybe a piece of metal sitting in a blacksmith forge. When that metal is cold, it's just black, right? But as you turn up the heat, first it starts to glow this dull red. Then as it gets hotter, it turns orange. Crank that heat up even further, and it becomes white hot. And finally, at the absolute extreme, it turns a searing blue-white. So why does this actually happen? Well, heat simply makes atoms vibrate, and those vibrating charges create light, or electromagnetic waves.
And there's this beautifully simple, elegant rule here. Hotter objects mean faster atomic vibrations, and faster atomic vibrations produce higher frequency light. Moving from red, which is a lower frequency, up to blue, which is a higher frequency, makes total intuitive sense. And the absolutely crucial thing to remember is that 19th century physicists understood this foundational relationship perfectly well. Everything tracked flawlessly with their classical physics, right up until they tried to measure the invisible light just beyond blue.
Which brings us to Section 2, the Ultraviolet Catastrophe. Basically, the crime scene of physics.
See, the physicists of the time had this trusty mathematical formula they relied heavily on, called the Rayleigh-Jeans law. This was their absolute best equation. And you know what? It worked flawlessly for predicting the energy of low-frequency light. When they applied it to red light, or invisible infrared heat, the math and the real-world measurements matched up perfectly. But the very second they used this exact same, highly trusted formula to predict how much high-frequency ultraviolet light a hot object should emit, total, absolute disaster.
The absurdity of the situation here was just staggering. According to the rock-solid classical physics of the day, the math declared that a hot object should emit an ever-increasing amount of energy at very high frequencies. What that basically meant in practice was that anything giving off heat, a stove, an oven, or that warm cup of coffee we talked about earlier, would just blast you with deadly ultraviolet rays. Your own body heat would vaporize you. But obviously, reality proves there is zero danger. You can sit there and calmly drink your coffee totally unscathed.
The math quite literally pointed straight up to infinity. It predicted a physical impossibility: infinite energy radiating from a simple, everyday hot object. And look, this wasn't just some minor rounding error. It was a fundamental break in reality. The scientific community was thrown into an absolute panic over this glaring contradiction. They even gave it this vivid, dramatic name: the Ultraviolet Catastrophe. They thought they had the perfect laws of the universe, but reality was clearly looking at those equations and saying, nope.
So, moving to Section 3, Planck's desperate trick, or fixing the broken universe.
How do you even go about fixing a broken universe? Well, enter a German physicist named Max Planck in the year 1900. Now, Planck wasn't some radical rebel trying to upend all of science. Not at all. He was a very careful, highly conservative detective who literally just wanted to fix the math by any means necessary. I actually love this quote from Planck himself. He called his own solution, and I quote, an act of desperation. He didn't even believe his own revolutionary idea at first. He viewed what he was doing as merely a mathematical trick, just a way to fudge the numbers so the formula would finally stop predicting infinity and match the actual data. He had absolutely no idea he was about to rewrite reality.
And here is the exact vocabulary word that changed the universe: quanta. Planck made this incredibly radical assumption. He assumed that energy is not continuous. It can't just be any random flowing value. Instead, energy has to come in tiny, discrete, indivisible packets.
He called these chunks quanta, which just comes from the Latin word meaning how much.
And this brilliantly illustrates the whole concept. Think of classical physics like a smooth ramp. On a ramp, you can place a ball at literally any height you want. It's completely continuous. There are infinite possible positions. But Planck's new quantum universe? It's like a staircase. On stairs, a ball can only rest on step 1, or step 2, or step 3. It cannot exist hovering in between the steps. Energy, Planck proposed, only moves in these specific, discrete, sudden steps.
So what's the actual size of those quantum stairs? Well, it's determined by this massively important, incredibly tiny number, 6.626 times 10 to the negative 34th power. We call this Planck's constant, usually represented by the little letter h, and it defines the exact microscopic size of those energy packets. This makes it one of the most fundamental numbers in the entire universe. It is literally the foundation of how energy operates on a microscopic level.
Section 4. Saving the universe. The resolution.
So, how did this tiny, desperate mathematical assumption involving a staircase neatly solve the high-frequency ultraviolet problem and save classical physics from itself? Well, because of Planck's math, the size of the energy packet is directly tied to the frequency of the light. So, low-frequency red light, that requires very small steps, just small packets of energy. But high-frequency ultraviolet light, that requires a massive step. A huge quantum packet of energy is required just to emit a single spark of UV light.
So the crucial point is this: at ordinary, everyday temperatures, most vibrating atoms simply do not have enough total energy to produce even one massive quantum of ultraviolet light. They just don't have the juice. It's exactly like trying to jump up a massive flight of stairs when your body can only physically lift its foot 1 inch off the ground. You just can't make the jump. And because of this, hot objects safely emit almost no ultraviolet light, exactly as we observe in real life. Boom! The catastrophe completely disappeared. Planck's mathematical curve perfectly matched the real-world measurements.
Which leads us to Section 5. The quantum door opens. The legacy.
Now remember, Planck thought this was just a neat little math trick to fix a broken graph. It took someone else entirely to step through that quantum door and realize what this actually meant for physical reality. Fast forward 5 years to 1905. A young, totally unknown patent clerk named Albert Einstein looks at Planck's work and decides to take quanta completely seriously. Einstein proposed something totally mind-bending. He said, if energy comes in quanta when it's emitted by an atom, well, maybe light itself is made of these tiny chunks. It's not just a continuous wave like everyone thought. It's a stream of tiny particles. That was the birth of the photon, and with it, the true birth of quantum mechanics. Planck's little act of desperation earned him the Nobel Prize in 1918 because entirely by accident he had discovered the underlying source code of the universe.
So what did we actually learn today? Just look at the incredible journey we've taken in this explainer. We saw how the old classical laws were completely broken, predicting absurd, infinite energy coming off a simple hot object. We saw how Max Planck stepped in with his desperate quanta staircase solution just to perfectly match the math to reality. And we witnessed how this specific, catastrophic failure of classical physics gave birth to the entirely new, weird, and wonderful field of quantum mechanics. But before we go, I really want to leave you with this final, provocative thought. Planck's constant is unimaginably small, right? Which is exactly why we don't notice the stairs of quantum mechanics in our everyday continuous lives. Everything just looks like a smooth ramp to our giant human eyes. But what if Planck's constant were much larger? What if that tiny quantum step was, say, the size of a baseball? How weird and glitchy and jumpy would our everyday reality actually be? Think about that. Thank you so much for joining me on this explainer. Keep asking those big questions, and I'll see you next time as we continue to unpack the universe.